Hi there, I'm Brendan Burns, and I'm going to be doing a deep dive on a recent outage in the Azure Resource Manager service. With me is Benjamin Pannell, SRE lead for the Azure Resource Manager. I wanted to start with a summary of the impact. The Azure Resource Manager, or ARM, is the gateway for all resources that are being created in Azure. It acts as a central point for access control, policy enforcement, and other management operations for both short-running and long-running asynchronous operations from our customers. Now, the duration of this impact was about 35 hours, and it affected 3% of the requests globally. In particular, it affected certain Azure customers who experienced timeouts and other failures for long-running management operations. It also had some follow-on effects for higher-level Azure services, which themselves call into the Azure Resource Manager for implementing their services. You can see here the primary regions that it affected. Azure spread around the world, and this is only a small subset of our regions. There were some marginal impacts on other regions around the world, but they weren't significant. Before we go too deep into the details of this outage, I wanted to introduce ourselves. I'm Brendan Burns, Corporate Vice President for Cloud Native Open Source and Resource Management in Azure. I've had over a decade's worth of experience with distributed systems and building cloud-native infrastructure, including co-founding the Kubernetes project and being responsible for a number of different cloud-native applications and control planes within the Azure public cloud. And with me is the lead of the Azure Resource Manager SRE team, and I'll let him introduce himself.
My name is Benjamin Pannell. I'm the technical lead for Azure's control plane SRE team, as Brendan mentioned there. I spent 4 years working with a bunch of absolutely phenomenal folks who have been involved in trying to improve this platform and a bunch of other ones in the control plane, and it's been one hell of an interesting journey. Prior to that, while my credentials are nowhere near as impressive as Brendan's, I've got the better part of a decade worth of software engineering experience, developing everything from mobile applications and Windows desktop apps, all the way through to embedded software applications on embedded devices, for vehicle tracking, web applications, monitoring platforms. Hi to the folks in Demonware at the back there, and most recently, the control plane services on a global cloud. It's been a hell of an interesting journey, and I'm going to delegate to Brendan for the first half of this talk, and I'll pick up with you in a moment.
All right, what can you expect from this incident presentation? Well, the first is you're going to see the full incident review used by the internal teams to learn from this outage. Furthermore, you're going to learn information as we learned information, so you can help understand how we went about root causing and understanding what the problem was. Now we're going to have two different kinds of information we're going to help share and identify. The first is context, shown in blue boxes like this, that helps you understand what's going on. And the second is exacerbating factors, which made things worse than we might have otherwise predicted, and they're shown here within this red box. All right, we're going to start with before the outage. A little quick overview of what you need to know about the system as a run-up to the start of this outage. All right, let's start with an overview of the system architecture. Azure Resource Manager consists of customer requests coming into a web tier where they're stored into a storage queue, and then in the background, asynchronous workers pick up those long-running jobs and execute them on behalf of the customers. Now, of course, because we're spread around the world and we need to be redundant, we have the similar stack in every single region where Azure is present around the globe. And of course, because we want to be resilient to regional failures, whether in storage or the web tier or the worker roles, we also do cross-connected topology so that if, for example, the workers in one region fail, the work will be picked up by workers in a different region. This helps ensure resiliency for our application in the presence of partial failures. We also conduct deployments of this application in batches over different time periods so that we can ensure that if a bad rollout is happening, we can stop it before it impacts the rest of the world. Okay, in the lead up to this outage, one of the things you need to understand is that we were in the midst of updating a legacy component. We were introducing a change to improve support for automated new region buildouts, and it targeted a legacy job type. The change was introduced using feature flags so that we could roll forward and roll back easily, and it relied on a new configuration system, but one that we had used elsewhere within our code base. We had also a full end-to-end test suite it was passing, and it included new tests to cover this change. So we really felt like we had covered all of our bases. However, a transitive test dependency that was included in the environment for the unit tests and was required by this code to function was not present in the final deployment artifacts. But of course, we didn't know this at the time. All right, so let's take a look at the timeline of the rollout of this change. The change was introduced into source code and merged into our repository on the 10th of December last year. Now, Azure teams pause feature rollouts around the holiday time to help reduce outages, both for our engineers and our customers during the winter holiday period. So in fact, the rollout of this change started about a month after the change itself had been introduced. This delay meant that engineers who had made the change, they'd lost context. They'd had a whole month of other things going on in their lives, and lost context on the risks of the change or even awareness potentially of the details of the change by the time it started to roll out. It went out first to a low traffic region and then proceeded with gradual exposure to medium traffic, high traffic, and eventually the rest of the world. All right, now the stage has been set. We have a good understanding of the Azure Resource Manager architecture and the details of the change that led up to the outage. Now let's start talking about the outage itself, how we detected and then responded to the first signs of trouble. So Azure services often pair regions together for resiliency. You can see here the worker tier is using job stealing to provide redundancy in case any particular set of workers go down. Now, in certain circumstances, we've actually arranged this such that there's multiple regions paired together and stealing work from each other in this sort of lattice framework. And what you can see here is that in this specific case, this configuration was implemented for West US, East US 2, and East US. Now, these regions become important because West US and East US were the first set of large paired regions that got this rolled out as it was coming out. Now, Azure services use synthetic monitoring to continuously test our services from the perspective of the end user. This outside-in monitoring sends requests from agents and accounts that we control into the service in the same way that the customer does, and checks to see if those requests are successful. In this way, we can understand problems that a user might be seeing that our existing internal monitoring might not otherwise notice. It allows us to spot deviations from the expected behavior with confidence. Now, about 8 hours after we updated West US and East US 2, our synthetic monitoring started failing. We responded to noticing these failures by tracing through the execution of the failed requests in order to understand better what was happening. We do this using an internal version of Azure Monitor Logs that maintains about 40 petabytes of data and allows us to execute complex queries across all of this log data in a handful of seconds. This better enables us to synthesize both the requests coming from the monitoring agents as well as the behavior of our internal systems to better understand what's going on. However, there were complexities in this case that confused our response to this particular outage. In particular, at the same time as we saw the failures in our synthetic monitoring, we were also seeing some errors in our downstream resource providers. ARM is an API gateway for a collection of backend services that we call resource providers that do the actual work of implementing virtual machines, network resources, or others. And at the same time as we were seeing monitoring problems in our own monitoring, we were starting to see downstream errors, and in particular 404 not found errors coming from a particular resource provider, the network one that was responsible for network resources. These cause failures in long-running operations, including deployments and deletions. But in fact, they were symptomatic of the problem rather than being the actual cause. But the fact that we were seeing these errors at the same time led to some confusion in our incident response. Now, another confusing element, or another compounding element, was the fact that we were not actually just having our own workers running against this job queue. We're actually in the midst of rolling out a new version of this microservice, a complete ground-up re-implementation that we call vNext. So simultaneously with our legacy workers pointed at the job queue, we also have a percentage of the work that's being done by our vNext worker. And obviously, as on-call engineers, we are always looking for oddities or differences in the system that would lead us to understand what's happening. And in particular, we saw a significant increase in job duration in the regions where there is impact, and the CPU spiking to 100% on the vNext workers. There was also significantly more pulsing or immediate scheduling without the job queue of work that only happens when there is available CPU or worker cycles available to the jobs. Now, all of this led us to believe that the problem was originating with this vNext worker. Now, I think we've all been involved in incident responses where our first reaction is to blame the new thing. And in this particular case, it seemed likely that the vNext version of our worker was causing the problem. So we decided that we should remove them. They're easy to remove from the system. And so we decided to remove the vNext workers. Now, we observed the expected drop in CPU, obviously, as the vNext workers are no longer consuming the CPU at 100% when they're not processing work. And we also saw a drop in job duration, which confirmed our expectations that it was, in fact, the vNext workers that were to blame. But the true fact is, removing the vNext workers actually only removed the only workers that were actually processing jobs at all. So it exacerbated the true impact of the problem and of the incident. But we didn't know this at the time. Now, the reason that it was hard to see that removing the vNext workers didn't actually have the desired impact is because we actually made two changes simultaneously. We removed those vNext workers, but of course, because they were taking up some of the capacity for processing jobs, we simultaneously added in more capacity to our legacy work queue, to our legacy workers, to process the jobs and offset the loss of capacity from the vNext workers being removed. These two changes simultaneously caused us to have a confusion around which one was actually causing the improvement in our metrics. We assumed that removing the vNext workers was improving things, when in fact it was the addition of these new legacy workers that didn't have the problem, as you'll see later on, immediately, that started processing work and started an improvement in the system. Because we had confusion between these two changes at the same time, we confirmed our own bias that it was the vNext workers, our own faulty assumption that it was the vNext workers that were to blame, and we could not tell the difference between which actual change was the cause of the effect that we saw in our monitoring. Making two changes simultaneously makes it significantly harder for engineers to determine which one had the positive impact, and in that state, there's a tendency to assume that the change was the one that you thought was the correct one, a sort of confirmation bias of your own opinion. And now I'm going to hand off to Ben, who's going to take us through the rest of the incident.
Thanks, Brendan. So you've obviously now seen the initial run-up to this. You've seen a little bit about the background of the service, and hopefully you've got a good idea of what's kind of happening at the high level in terms of symptoms. And I want to talk a little bit about how the properties of the system that led us to develop that faulty assumption and get that faulty assumption confirmed, in our view, contributed to an exacerbating degree of impact, and then dive into how we approached resolving that and starting to learn from it. So before I dive too deeply into that, I want to talk a little bit about the timeline so far. Our initial detection happened at about 11:51 UTC on the 13th of January this year, and that was detected with synthetic monitoring, as Brendan mentioned earlier. It took us about 7.5 hours or so before we finally got to the stage where we were doing our initial mitigation steps, where we developed that understanding that there was the vNext workers playing a role here. And this was contributed to by the fact that we did a shift change a couple of hours before that. We brought in additional experience, and these folks were able to spot the oddities there that we hadn't been able to spot earlier. Over the course of the next 4 hours, we watched the telemetry that we discovered over the course of that shift change progressively get healthier and healthier, and by midnight, we ascertained that we believed the situation had been resolved. We'd mitigated the issue. What we didn't realize at the time, though, was that behind the scenes, our automated deployment system was still processing a deployment train, and it was rolling out to the second half of the world. Now, this was something that continued automatically because at this point in time, the majority of regions were still healthy. Our telemetry was still indicating that everything was fine. We had a single region's worth of minor impact. And our engineers who reviewed this looked at it and said, well, we believe we understand what's going on here. It's our vNext workers. They haven't been updated yet. It's unrelated to the release. We'll allow that to continue. Unfortunately, about an hour later, we started getting reports that we were seeing issues in other regions globally. So at this point, our engineers did the obvious thing and decided to apply the same mitigation we had applied earlier. We removed our VNext workers globally, and by 2 o'clock UTC, we had completed that transition. Unlike earlier, we didn't decide to scale out in this case. Our engineers had looked at the situation and said, well, we understand that the VNext workers are additional capacity, they're experimental, we're expecting to remove them if there are any issues, and one of the aspects of how we've provisioned the legacy workers means that we should be able to lose over 50% of our capacity and still process jobs without any problems. So in this case, we continue to operate without the VNext workers. We didn't scale up any new legacy workers. And as a consequence of that, what we started to see was this interesting correlation between the latest release rolling out and the regions that started to see impact. So we moved from a single region of impact, West US, and started to see new impact appearing in regions that had just recently been updated. What was really interesting about this correlation is that it didn't actually appear previously. This was the first time that we'd started to see a clear correlation between the latest code being released and regions being impacted. And what I really loved about this incident is that every time I talk about it, every time I present about it, we learn something new. And so in preparing the slide deck, one of the things that became visible is that the fact that we removed those VNext workers, something that tangibly reduced the resiliency of the system and increased the impact, actually contributed significantly to making this correlation very visible. So it's one of those things where you change state, and that highlighted the problem, but it wasn't necessarily something that was in the best interests for our customers here. Now, as soon as we found out that there was this correlation, we decided that we should roll back. And rollbacks are a really interesting thing to do. You obviously want to do them as quickly as possible. You want to try to minimize the impact for customers, but it's also a massive state change that you're applying to the system. Now, as confident as you can be, you've seen here, we're obviously relatively confident the VNext workers are playing a role. You can still be wrong about that. And when you're dealing with a system that's already in a degraded state, adding a state change, adding something that may result in restarting instances and reducing your capacity is a very large risk. So something that we do to try to minimize that risk is we do a we roll out in the same phased approach as we would for standard deployment. Canary, low traffic, medium traffic, high traffic, rest of world. And the idea here is that it gives us an opportunity to identify if there is compounding factors with that rollback that might mean that we need to stop that or change our theories about what's going on in the system. Of course, you need to balance that as well against the fact that you've got customers that are impacted. And one of the things you're aiming to do here is minimize customer impact, mitigate as quickly as possible. So what we decided to do in this context was we decided to target our 7 most heavily impacted regions as part of that first batch. So alongside our Canary, the most heavily impacted regions got updated as well. And by 6 a.m. UTC, we'd finished that targeted rollback, and the vast majority of customer impact at this point was mitigated. It took us another 12 hours to finish the rollout globally, and over the course of that time, our engineers were engaged with partner teams and customers on the bridge, making sure that things were moving forward, that we were minimizing customer impact there. And at 6 o'clock, we were confident that we'd mitigated the vast majority of that customer impact, that everything was working correctly at this stage. But our engineers remained engaged on the bridge for another 8 hours, just double-checking things, dotting I's, crossing T's, making sure we didn't see any further regressions there, and then remained engaged off of the bridge for another day, just making sure that everything was sorted until we understood what was going on. So now let's talk about understanding what was going on, because mitigation is obviously one side of the coin here, but if you don't understand why your system failed, you're unable to go and fix that, move forward, and make progress. And systems that remain stagnant are stagnant with the existing problems that they have there as well. You're obviously trying to consistently move forward, improve the quality of your services. So figuring out how you can go and manage investigations while dealing with a relatively high impact outage and manage your customer comms, manage your on-call expectations is a challenge. And there's something that we did here that really helped out significantly, and that was creating the space for our engineers to do this job separately. So I mentioned here that mitigation and investigation are kind of 2 separate work streams. As the on-call, you're often expected to focus on mitigating the issue as quickly as possible, on communicating to customers, on dealing with any queries from partner teams and helping them mitigate their impact. That's in your interest in the short term as an organization, but in the long run, you really do need to understand what's going on here. And you want to do that ideally as quickly as possible so that you can fix the issue, you can deal with, or you can gather information while that's easily available and at hand. And so what we did in this situation was we asked our SRE group to focus on the investigation side. We separated them out from a portion of the on-call, let the on-call engineers focus on the immediate mitigation, and instead had these investigators sort of sandboxed off on the side to go and work on that. And this allowed them to focus on investigating what the current state of the system was, like really drilling down, building a model of what was going on inside the system that we didn't understand, and developing and testing hypotheses that could try to explain what was going on here. So the first question we started out with was, why was West US the first region impacted? Like at this point, we deployed to the first half of the world. We had 26 regions at least updated, and yet we only had a single region's worth of impact in West US. And so our engineers started trying to dig into what was going on here, what architecturally was different about West US compared to all the regions that hadn't been impacted. And this is where we found out that in this specific configuration of our deployment trains, West US and East US are the first two large paired regions that are updated as part of the same train, or as part of the same daily batch. And this was really interesting because when you kill off workers in two of these regions, or when they stop processing work correctly, our resiliency model results in East US continuing to have work processed by East US 2, its redundant pair that hadn't been updated yet, but West US loses both its primary and secondary job processing capacity. So that explained why we're starting to see impact there, but we do have canary regions that are deployed in pairs as well. And so the question was, well, why aren't we seeing this impact in the canary regions? They've been deployed for over a week at this point, and everything's still working fine. And what was really interesting to find out in hindsight was the specific job type that was being used here, the thing that caused problems, was something that didn't have enough traffic in our canary regions to actually manifest the problem. And we'll dig into exactly how that manifested later, and hopefully it'll make a little bit more sense as I make that assertion. The next question we wanted to ask is, like, we've had on-call engineers looking at this for over 24 hours at this point, trying to understand what was going on. They were looking visually to try to identify any kinds of correlations between this reduction in successful jobs being processed and any errors, anything that could explain what was happening there. And really, they struggled. Like, a lot of our telemetry showed what appeared to be just this general reduction in the amount of jobs being processed, a general reduction in web traffic, a general reduction in CPU load. And so the system just looked like it was slowing down, that there was less to do. And yet we obviously knew that there was customer impact here. So we were trying to understand what exactly was going on. And what was really cool is as soon as we found out that there was this clear correlation between the release, so the previous release and the new release, we were able to start applying some statistical analysis techniques to understand exactly what had changed there. So looking at were there shifts in medians and variances for some of the errors that we were seeing. And the errors in question here were really a needle in a haystack. They were 0.1% of the total number of errors being logged by the system at any point in time. And what we were able to find with these statistical techniques, comparing the before and after, so developing a baseline for our previous release and then looking at what the latest version had done, was a very, very low volume event corresponding to crashes in our workers that had increased by about 100-fold. Now, this event still accounted for a very low volume of events. It was about 1% of the fleet that had been impacted over the course of the last 24 hours, and that's well below what we would intuitively expect to cause any kind of customer impact from a capacity perspective. As I mentioned, we've got a significant amount of over-provisioning here to support the loss of single regions without any expected customer impact on that front. And what was also interesting is that these errors only occurred several hours after the first indications of customer impact, so after our synthetic monitoring had failed. So there's a massive trailing indicator of what was going on, and yet it was the only thing that sort of stood out as being particularly different between these releases, or between the system working in a healthy state and an unhealthy state. So we started to ask, great, like, why were we seeing these delays? Why were these errors delayed? And specifically, why were we seeing workers start up correctly, appear to process work for a period of time, and then several hours or even a day later end up crashing with these errors? It was a particularly interesting thing to see. The other thing is that looking into these errors, we noticed that the stack traces highlighted that these errors were being thrown inside our job processing loop. And our job processing loop is wrapped in a try-catch block. The expectation is that any errors that are thrown there, any exceptions that are thrown there, should be propagated as a metadata failure on the jobs. The worker should then pick up a new job and continue processing. And we'll attempt to retry those jobs. The expectation is that these things should not cause our workers to crash. And yet, clearly, we were seeing this happening. All of this meant that the engineers investigating this sort of scratched their heads and said, all right, well, it doesn't sound like this should be possible, but it's clearly happening. Like, what's going on here? Like, the symptoms that we're seeing, these delays for customers, the jobs timing out and failing at the end, match what we'd expect to see if we had a very large number of these crashes, if we were losing a significant portion of our worker capacity, and yet we're only seeing a handful of these things failing at any point in time. So of the thousands of workers we have globally, we had maybe 5 down at any point in time. And so it was a very interesting thing for us to try to reconcile. Now, I can try and drag this out, but instead of bearing the lead, I'm going to focus on what was actually going on. Now, when our engineers were looking at this, they looked at the stack trace, and one of the engineers looking at the stack traces went, aha, I've seen a PR that looks like it's related to this. Let me go and dig in. And so I'm just going to show you like the leap that they made here. over here on the right, you'll see kind of a representative version of what this legacy job looked like, and specifically the context of the change that we were making there. So you can see we were introducing a new configuration system. The idea here was that this new configuration system would provide metadata required to support automated new region build-out. And we had feature flags in place to decide whether we used that or whether we used legacy hard-coded information for that. The exception that was thrown, and I'm sorry that this is not rendering great, it's luck of the draw in many cases. The exception being thrown here was a directory not found exception being thrown where we tried to initialize that new configuration provider, and that was caused by the configuration files that were required not being present in our final deployment artifacts. They'd been brought into the test environment by that transitive dependency, but when we actually got to production, they weren't present there. And what was interesting here is that we'd used a static initializer to set this up. For performance reasons, these jobs are initialized many times, and being able to store that in a single place meant that we were able to gain a performance advantage in our test suite. And we also used reflection to dynamically instantiate this class at runtime. The use of reflection in .NET meant that when that exception was thrown, it got wrapped in a type initialization exception. This is a low-level exception in the .NET runtime, and it's used to indicate that there was a problem instantiating a core type or any class, any kind of instance. Interestingly, that's a non-recoverable exception if you look at the standard. Another interesting aspect of this was that because the initialization, or the exception was thrown in that initialization logic, it bypassed any of the feature flags that we'd put in place. So although we'd only enabled our feature flags on Canary, we ended up having impact in production environments as well. And that was obviously not intentional. That was not what we wanted to see. But it's a really interesting indication of how these little patterns that are very easy to skim over as you're code reviewing can come back to bite you. Now, those jobs that get executed are hosted in a worker slot. And so I want to talk a little bit about the worker slot because it adds some really interesting context to how this failed. So conceptually, the worker slot is essentially an infinite loop. Inside the infinite loop, we've got this try and catch block. And what happens here is we'll pull a job from our available job queue and then attempt to process that. And if there's any exceptions, the idea is that we'll log those, we'll mark the job as failed in the metadata, and move on to the next loop iteration. But what was interesting here is I mentioned that those type initialization exceptions are considered a fatal exception in the .NET runtime. And so the idea here is that they're not recoverable. You're not able to safely progress inside your runtime once you've encountered one of those exceptions. And so what you're supposed to do is you're meant to bubble that up, let the process crash, and then let the external orchestrator come and restart the process. It's the only way to get back to a safe state inside your process. But what was also interesting here is that because it was classified as fatal, and because we had that expectation of bubbling it up immediately to the top level of the process, throwing the exception there, logging it there, and then crashing immediately, we didn't end up logging any of these exceptions. And what this did was it meant that although these things were firing, we didn't see any of these signals. They weren't available in our telemetry, and our engineers that were sitting there looking for something to be increasing, an error rate to be increasing somewhere, weren't able to find anything when they were looking at the telemetry earlier in the incident. There's also a work dispatcher, and so these job slots are orchestrated within a work dispatcher. The work dispatcher's job is, amongst other things, to manage queuing in memory, pulling jobs from a centralized queue, and then actually running, in this case, several thousand job processing slots. And the way that that's implemented is using the .NET Async framework. And essentially what we've got here is you spin up a bunch of tasks, add them to a list, and then we use the task when all API to coordinate waiting on those to complete their execution and to bubble up any exceptions. Now, we use the async functionality in .NET because it is much more lightweight than threads, for example, when you're talking about a very I/O-heavy workload, which is exactly what our workers are. And it provides a very nice abstraction over managing high concurrency systems. Obviously, leaning on task when all here to catch those exceptions is a relatively standard industry practice. That's the way that most people would traditionally do things. But what's interesting about task when all is that it's designed for fan-out operations. It's designed for things that aren't necessarily very long-running, and much like promise.all in JavaScript or join in Rust's features framework, what you'll find is that the idea is you fan things out, you collect the results quickly, and then you move on to doing some additional work. In this case, we were using it instead for something that was very long-running. The idea was that this would last for the duration of the process's life cycle, and so we weren't really expecting to ever reach that terminal phase unless we were shutting down the process or everything was crashing. And there's a really interesting property of the way the task when all works, which is that it will not return any results, whether successful or raising exceptions, until every single one of those tasks has completed. So if we look at this graph here, this is a representation of kind of how that plays out. You start out the function, you spin up a large number of tasks, and then regardless of how many of those die over time, you remain in that active phase with all of these running tasks right up until the very end when everything is crashed, at which point you finally raise these exceptions. And this plays out really interestingly in this specific case. Specifically, we had this legacy job type now that was failing, or acting as a poisoned message in this work queue. And what ends up happening is that because we start out with several thousand worker slots and a probability of about 0.05% that we're running one of these legacy jobs at any point in time, the initial probability that at any point in time one of these job slots is processing a poisoned message and dying is up around the 75% mark. So you very rapidly burn through your available capacity and your workers and reach this critical capacity threshold where you're no longer able to process enough jobs to keep up with customer demand. But as you move through that, you start to lose available capacity to process these jobs, and the probability that you're going to run into any one of these, that it's going to kill a slot on the worker, rapidly degrades until you reach that 0.05% probability. And this massively extends the tail and means that while you may lose your available capacity much earlier on, it may take several hours before you actually see the worker crash. And that explains those massive delays that we were seeing. I want to talk a little bit about some of the things we're doing to improve. This isn't an exhaustive list. We've shared this with a bunch of teams internally. We've presented it across the organization, and there's clearly a bunch of folks that have taken their own inspiration and stuff to their own teams here. But I want to talk about a couple of things we're doing within Azure Resource Manager to try to improve this. The first is reducing transitive test dependencies. The idea here is let's close that gap between production and test and try to reduce the opportunities for things to sneak in there. The second is reducing our reliance on static initializers. They're really convenient for managing singletons, but they're also a big risk for this sort of reason. So trying to move away from that as much as we're able to and find better ways of managing that life cycle. Next thing we're doing here is trying to improve visibility to uneven workloads. So you saw earlier that EastUS2 picked up work for EastUS, and that was a shift of work from one region to another, but it wasn't something that was immediately visible to our engineers when looking at things. So when they were looking at, is our job system healthy, that wasn't something we were putting front and center and making very easy for them to see. The other thing is it was very difficult for us to monitor for. There's a couple of additional layers of context here. One of those is that we didn't actually stop processing all jobs from these workers. We stopped processing jobs from a couple of specific work streams. Those were the workers that were killed, while other workers continued to function. They hadn't received any poison messages. And as a result of that, the monitoring we had in place didn't actually spot that there was a shift in these workloads. It didn't spot that there was a problem with the workers not processing the work that they were expected to. So what we're trying to do here is encode some of the system invariants that we expect. One of those, in this case, is this idea of fair work distribution. You do work stealing between regions, we expect that they're going to pick up a fair number of jobs on either side. And the idea here is that by encoding those invariants, the things that should never be violated, we should be able to very easily drive a high-quality bar for our monitoring, reduce the amount of noise that we get, but also really increase sensitivity to things that are potentially impacting. Those points where the system moves outside of our design domain and into a domain where we don't understand what it's going to be doing and where there's potentially increased risk. The other thing we're doing here is working with various teams. So there's over 300 teams across Microsoft and several teams outside of Microsoft that build on the Azure platform to encode the requirements around that cache expiration for operation metadata, and specifically the operation status that resulted in customer impact when that network system expired items before the jobs were complete. The idea here is that this increases resiliency by making sure that those pieces of metadata are available for a longer period of time, and certainly until the job itself expires. We can help ensure that any degradation in performance doesn't reach a cliff, at which point we drop off and suddenly start impacting customers way more than we would otherwise do. It gives us a little bit more headroom to deal with the sort of degradation in future, and potentially buys us some time to mitigate these things should something like that happen. We're also looking to improve our visibility into queue pickup delays. And now this is a really interesting one, because while we had layers of visibility into that, it was aggregated in a way that made it very difficult for our engineers to understand where this problem was occurring. And because a lot of the stuff that was getting picked up, again, like we saw a reduction in the rate of pickup, because of the way that this stuff was aggregated, we actually didn't get a good signal that there was increased delays in the system. The stuff that was being picked up normally wiped out any of the discrimination that we would get there and just managed the average and the median, or drove the average and the median in a way that masked a lot of this issue. So we want to be doing a better job of discriminating those differences between different queue pickup paths to make sure that we can understand what's going on inside the system here. And finally on this set, talking about removing the reliance on task when all. So obviously this is something that is relatively extensively used. We've worked with a bunch of teams to identify areas where that's a risk. And we're currently using a hybrid approach that uses task when any to ensure that we fail fast. And then we're using task cancellation tokens to propagate that cancellation information to ensure that we can rapidly shut down if there is a problem like this. If you're interested to find out more from that, come and find me in the hallway or something. I'm happy to talk about it some more. But we're also trying to work with the underlying platform teams, so the .NET Framework framework team to try and find ways that we can help improve the ergonomics of something like this in the future. Now, I've got a couple of closing thoughts, just some things to think about, some of the things that we were thinking about after going through this process. The first of them is outage severity is something that you might not always be able to measure exclusively through your SLOs. Now, our platform is very API heavy, so while we do back-end asynchronous work on workers, a lot of our focus is, or a lot of the potential for customer impact is on that front-end API. And as a result, outages in that web tier disproportionately impact customers, and it's disproportionately immediate in a way that our workers aren't necessarily. So when you start doing an apples-to-apples comparison and trying to compare a web tier outage against a worker tier outage, there's this massive bias towards prioritizing web tier outages in any of the numbers that we currently use for that. As a result of that, this outage, while it was very, very impactful for customers and represented a significant risk to them, wasn't something that was necessarily as visible in our SLOs, although clearly, like, our intuitive understanding here would indicate that it was something that needed prioritization. So my question for you is, how are you identifying things like that? How are you identifying the outage that, according to all of your telemetry, doesn't seem like it was that bad, but honestly really needs you to dig in and understand what was going on here? Like, where do those things happen? And how are you updating your SLOs once you learn that to better encode this understanding of your systems, the human understanding that is so critical to our being able to operate these things? The second interesting observation here is that you're incentivized to optimize for your common failure modes. So I mentioned that we're API heavy. That has a secondary knock-on effect. The effect is that we're incentivized to improve our ability to respond to, understand, and deal with failures in our web tier far more so than we were on our worker tier. And that meant that when we encountered a novel failure mode in a low-level library that we depended on, we weren't as prepared as we would have liked to be to investigate that, to understand what was going on, and to respond effectively. So how are your organizations going and identifying these risk areas? You heard Laura yesterday talk about an interesting database failure where they had a component that everyone had forgotten even existed, stopped functioning, the monitoring didn't work for it anymore because no one had been paying attention to it, and they needed to go from base principles and redevelop their understanding of what they were dealing with to be able to reason about this. So my question here for you is, what's a critical component in your execution path that hasn't had an outage in a while that people have maybe forgotten about? Like, how are you going to find those things? How are you going to make sure that those things are getting the investment that they need to continue functioning correctly in the long run, and that you can triage problems that occur in those components in future? And finally, and I think this is my favorite quote, potentially of all time, but certainly from safety science, is Dr. Richard Cook's quote, "Complex systems run in degraded mode." Now, that core component, that worker component that fundamentally failed here, or that masked those failures, buffered them, and resulted in a disproportionate degree of impact and lack of visibility into this thing, had existed in that state for over 8 years. It was used not just in our service, but a range of other services. And selection pressure at scale will eventually highlight those problems. It takes time, but eventually someone's going to ship a PR that pushes just the right buttons, slips through just the right cracks, and you're going to find out about this stuff. So what are your organizations doing to spot those things before they're customer impacting? Identify where those risks are, get the learning before you need to do what we've done here, and ensuring that you're actually mitigating these issues in depth, not just relying on symptomatic fixes, but actually understanding where the underlying issues come from so you can mitigate those problems there. And with that, I'd like to thank you very much. I hope that that was informative.